Okay, let's start a new topic, which is neural network basics, and it is N01, the class node. And in this hour, we'll introduce some basic concept of neural networks. And I think it is very important for you to understand the file in some other more complex neural network. So let's start. We run this class node, this CodeLab file in CodeLab server. So make sure you have the same version of TensorFlow if you run this CodeLab file in your own laptop or computer. Okay. In this hour, we will use a simple data set, which is auto MPG, stands for miles per gallon, and it's just a simple data set for demonstrate how neural network works. Okay, so here is the table, and there should be nearly 400 data samples, right? And they are all numeric data, but it is there's some thing run with this column, okay, called origin, and the target Y is MPG, which is we need to use some other features of a car to predict its corresponding miles per gallon. Okay, so most of the time we use the horsepower as the feature. Okay, if we only need one feature, but actually it has 9 different features. But an important thing is that the origin column, it stands for where's the country, okay, build this car. So it is categorical data. Okay, so we will first do something with this column. Okay, so the first thing is to take a look at this simple data set. Okay, so we figure out there are 6 data points, okay, which has missing value. So we simply just ignore those data points, okay, those cars. Okay, so here is the definition of the origin field. Okay, it is either a car in United States or Europe or Japan. So I think this is a very important function you need to know, which is get dummies, because it helps us to build features by using the calculated data. Okay, so it is one hot encoding, right? It is one hot encoding, so it will automatically transform your categorical data to one hot encoding data. So we have 3 new columns right here. So it is either 0 or 1. Okay, so that is one hot encoding. So currently the data table right now, they are all numeric. They don't have it does not contain any calculated data. Okay, so we use this data to demonstrate how neural network works. Okay, so the first thing is that usually when we collect data, it is sometimes not that easy for you to collect training data, okay, and validation data and testing data, right? So usually we have only one data set. So most of the time we will use this function train test split to randomly split the data into 2 different data sets. So right here the data set test size is 0.2. That means 20% of the data will be the testing data, and 80% data will be used as training data or validation data. Okay, so it is a very common way for us to train a model when we have only one data set. Okay, we randomly split it into two different data set. Okay, so here's the data set. Okay, so the next thing is we still need some statistics information about the data set. So we take a look at the training data set and draw very nice figures, right? So the MPG is Y, right? So we have some other features right here. So we can take a look at the scatter figure, okay, of Y and some other features, and also take a look at the distribution of each columns, right? And as we can see that we can see some trend, okay, some trend. If you take a look at the scatter figures, so I think it is promising to build a model to find the relationship between Y and those features X, right? So, and again, you can use the describe function to obtain the describe the statistic information of each features and target, right? We have mean values, standard deviation, and some other useful information. Okay, and of course we can we need to MPG is Y, right, and all the following is X, so we need to split the Y and X, okay, by using some functions right here. So after that, okay, we have 9 different columns as the feature and one single Y target map. Okay, and for demonstration, okay, we select the host power as the first feature, okay, X1. So the next question is we need to build some models to figure out the relationship between X and Y, right? But the first question is that do you believe that the X1, which is the horsepower, and the Y, which is MPG, are they linear? We don't know. Basically, we don't know, but it's worthy to try, right? So the first model we'd like to try is a very simple linear regression. So that is Y equals AX plus B, right? And for neural network, usually we don't simply just write the model, okay, in mathematic form. Usually we can draw a network to represent the model. So that is how it is drawn. For example, if you have only one feature, okay, which is the X1 right here, and you simply draw a circle and that is X1. So basically that is the input value, okay. Since we have only one features and one target value, okay, so usually if you model your data, okay, as A X1 plus B, basically A and B are parameters, right? Now weight. So when you draw the figure, weight are on the link, okay? So basically it means A times X1, B times 1, so that is 1, right? So we pass the data, okay, AX1 and B1 to a new circle, which is right here. So there are 2 arrows, right? So that is plus, okay, that is AX1 plus B, and it becomes Y. So you simply just use a figure, graph, okay, network to represent this specific relationship you want to describe between x1 and b, and we have two parameters, which is a and b. Okay, so at the left hand side, okay, we called it a layer. So x1 and 1 is the neuron, okay, it's a neuron in input layer, and y is the neuron at output layer. So we have n data point, right? So for this n data point, the first data, okay, which is I equals 1, will be feed into this network from the left hand side. So for example, if it's 5 and 7, so 5 will be, for example, okay, 5 will be right here, and y will be 5 times a plus b, something like that. Okay, so that is how we use a graph, use a neuron, okay, use a network to represent linear function. Okay, if you believe the relationship between x1 and y is linear, you can use this figure to represent your model. The reason why we use a graph to represent the model is that we believe a model, okay, I mean the data set in the real world, the relationship should not be linear and should be very complex. So we can draw a very complex graph to represent the model. Okay, so here's another example which I write here. If you think your model is linear, but you have multiple variables right here, okay, you have x1, x2, this one should be x2, okay, x2, x3, you have m features, and you want to represent a linear model with multiple variables. So that is right. So and of course we have some other ways to write the formula, right? We can use array or a matrix to represent w and x1 to xm, right? So in this case, the big X should be something like this one, okay? The weight right here should be like something like this one, and w1 to wm. So simply just use w and transpose, okay, times the big X, and it will be it should be this part, right? It should be this part. And usually we use the interception, okay, which is w0 or b, okay, we write it right here. But you know, sometimes we use another way to represent these things. It's in green right here. If we have additional one features, which is a constant value, which is 1, and we can put w0 right here. So in this case, we can simply just use w transpose times big X to represent the entire model, okay, which is more convenient, right? Which is more convenient. So we can simply just ignore the interception because we put it in the first element of your matrix. Okay, it really doesn't matter you use the first representation or the second one. Okay, it's the same. So when you want to draw the graph, okay, to represent this relationship, basically by using a neural network, you can draw it. You can simply put all the X right here by using the neurons, and put the corresponding weight on the links, right, and add them together. So that is add them together, so it becomes y. So it means simply this view graph, this figure, simply just exactly the same as this one. Okay, so that is how we use multiple variables, okay, on a linear relationship, okay, to represent the relationship between x and y. Okay, and of course by drawing different figures, okay, you can create a more complex relationships. So here is an example, okay. So so that means maybe that is so complex. So right here we have the input layer, okay, and again we use x1 to xm. So sometimes when we draw the figure, we can simply just ignore the 1 and the w0, okay, or b, because I think it's easier for us to draw the figure, okay. But it should have one additional neuron, which is 1, and its corresponding weight is w0. But sometimes we simply just to simplify the figure, okay, we ignore the interception, okay. So maybe we can have a multiple layer of the to represent the relationship. So we have input layer right here. So again, here we have a intermediate hidden layer, okay, and we design it has two neurons, okay. So take out the green weight, okay. So that means h1 equals x1 times w11 plus x2 times w12 plus x3 times w13, so on and so forth until xm plus wm. So h1, okay, h1 is something like that, okay. The weight is in green, okay, the weight is green. So maybe that is a point of view to describe the relationship between x and h1. And again, take a look at the purple links, okay. We've had another set of weight which is in purple, and it shows the relationship between h2 and x. And after that, okay, as mentioned, it is a complex relationship, so you can use another yellow weight, which is w1 and w2, and use it to connect x, y, and h1 and h2. So the relationship between x and y, we use two additional hidden neuron to represent a more complex relationship of x and h and y. So basically, it's right here. Okay, so after that, okay, after you know how to draw a figure, and then as a neural network user, you can draw any relationship between your input, which is x, and your output, which is your y. You can have multiple hidden layers. You can connect those neurons by whatever you want. But usually we need, again, although you can design a very complex neural network, but there are some still some rules, okay, which can help you to do so. But the very first thing I would like to talk about is if you simply just use if you simply just randomly connect neurons, okay, from input layer to several different hidden layers to the output layer, there's one thing you should notice is that it's right here. Okay, so if you that is your input layer, right? So that is your first weight. So you times your input layer and your first weight. So that is some the value of your hidden layers, right? So after that, you use this weight and time it with your the result of your hidden layer, and it becomes the y, okay? Make sure you notice that, okay? If you take a look at this equation. Okay, because when you do such kind of calculation, you can always calculate weight A times weight B first, and the result, for example, will be weight C. So basically, if your calculation or your design is pure linear, and that means WA can firstly times with WB and becomes WC, and it looks like you have only one single layer, which is WC, and its weight is WC, to describe the relationship between X and Y. So no matter how different the neurons you have in each hidden layer, and no matter how many different hidden layers you have, okay, if their relationship is pure linear, the result, okay, the result will be it will be I described it, the effectiveness of your design, okay, will be exactly the same as another neural network which has only one hidden layer. Okay, if you think, okay, I have two hidden layers right here, but if the design is pure linear, the effectiveness of your design will be exactly the same as another neural network which has only one layer, and its corresponding weight is WC. So when you design a neural network, okay, you have to make sure you add some nonlinear function in your neural network. Okay, so for designing a neural network, okay, so that is right here. Usually we request the designer to add some nonlinear calculation operation in your neural network, so that these things would not occur in your network. Okay, so most of the time we will add in our class, okay, we will add a circle right here, and this circle, of course, is what we call activation function, and there are several activation functions. We'll talk about them 2 weeks later, and so far you have to know that those activation functions are nonlinear function. So in this case, if we draw a circle right here, that means, okay, the Y value, okay, should be something like there's an activation function which is nonlinear, but inside it, okay, it is something like that. Okay, and the nonlinear activation function, okay, we have several candidates, but we have already have one activation function which is called sigmoid function. Okay, we use this sigmoid function in logistic regression, right? So this function is also called logistic function. It is sorry, it is a nonlinear function, right? So we simply just use your feature and transform the feature with your weight, and then we put the result into a nonlinear function to get Y. And of course, it is not necessary to use this structure. Okay, it's really depend on you, which is the neural network designer. Okay, if you believe your input and your output, which is your X and Y, and maybe they have certain relationship, and you can use such kind of nonlinear formula to describe the relationship between x and y, and you can use it. But sometimes it is not looks like this. It depends on the understanding of your how you understand your data set. Okay. And again, maybe the network is a little bit complex. So you have multiple inputs right here, and in the hidden layer, okay, you can design k different neurons right here. And for H1, right, it is basically something like this one, right? H2 is another neuron, and its value should be something like this, and so on and so forth. And if you have k neurons in a hidden layer, and notice that those weights, they are all different. So you have many different weights, many different parameters to describe the relationship between your neurons in the hidden layer, which is H1 to HK. And then right here we have another, which is something like that. Okay, this big edge is the collection of all the hidden neurons, the value of all hidden neurons, and use another weight, okay, to describe the relationship. And beware of that, we have circles right here, so that means actually we add some nonlinear function on these neurons and also right here, so that we can use those nonlinear functions to describe and this view graph, okay, this figure, to describe a very complex relationship between x and y. Okay, and it's really depend on you to decide how many different layers, and in each layers how many different neurons you want to put it into this hidden layer. Okay, and then we wish such kind of figure, such kind of network can help us to design different models. Okay, so the next thing is how do we use some packages, Python package to write our model, to design our model, and to train our dataset. Okay, so basically we use TensorFlow Keras, okay, which is a very nice Python package which is designed by Google. Okay, and it has some convenient functions for us to design the neural network. So here here's what I would like to introduce. Okay, so before that, you can see that the hidden layer right here, okay, we have k different neurons, and you can see that for example, for the H1 neuron, okay, it accepts the information from the input neuron x1, x2, and so on and so forth to xm. Right? So it has n+1 element, okay, to construct H1. Okay, so basically all of the neurons will pass the data, okay, through all the links to H1 to the neuron. Okay, and for all the other hidden neurons, okay, from H1 to HK, they do the same thing, although they have different weights. Okay, so such kind of structure we called dense. Okay, dense. or we call it dense layer, okay, because it accepts all the information from the left hand side to the hidden layers, to all the neurons in the hidden layers. Okay, that is called dense. Okay. Of course, there are several other different relationship between the left hand side layer and the right hand side layer, but most of the time we or for the simplicity, most of the time we use dense layer, okay, to accept all the information from the left hand side to the right hand side. And of course, there are some other layers. We will introduce different layers, different types of layer later. Okay. So again, I'd like to show you something that we talked about before, which is normalization. Okay, as you can see that the mean value and of different features, okay, they are quite different. The range of them are quite different, right? So we mentioned it before. Before you use your, for example, SVM model or linear regression model, we suggest you to perform standardization or normalization. Okay, we have explained the reason why we use those things. That is because when we do gradient descent, okay, the data, okay, after normalization would create a more we say a basin, right? When you perform gradient descent, okay, basically you calculate you will get a shape like this one, okay, that is a basin, okay. And as we mentioned before, you select a theta 0, okay, which is A0 and B0, okay, randomly, and we try to perform differential differentiation, right? Differentiation to find the smallest MAC value, right? And we like to show you that, okay, if you perform, so it's right here. We first talk about how to do normalization in neural network, okay, and we'll show you why normalization is an important thing in design when you design your model, okay. So if we like to do a very simple linear model, okay, so basically you should perform normalization first, and by using keywords, okay, TensorFlow keywords, you can simply just add one normalization layer on your input data. So basically you have to do this, okay. You have new normalizer, okay, which can normalize your data, and you put all your data, okay, your training feature to that normalizer, and that's it, okay. So when you draw the graph, okay, that means that is your original input, which is x1, and the normalizer, which act as a activation function, although that activation function is just some normalization process, okay. So we draw a circle right here. That means we apply normalization as an activation function on your x1, okay, which is a feature, and the output value should be the normalized value. We represent it as x1 prime, okay, and then you use x1 prime to perform your linear model at the right hand side, okay. So so we create two different models. The first one is without normalization, the second one is with normalization, okay. So here it is, okay. We have a simple feature which is x1, okay. The other is the MPG as target as y, okay. If we draw the scatter, you can see that the range of x and y is a little bit different. So that is the reason why we want to perform normalization, okay. Otherwise, if you use x and y without normalization, the best, okay, the best model, linear model, would be something like this one, right? So the slope would be quite small, okay, and it may cause some problem. Okay, we'll show you later. Okay, so here is it. Okay, here is the definition of MSE and the model. Okay, so let's take a look at the MSE, and that is A. Okay, that is B. Okay, we'll draw it in by using the contour figure. Okay, so the line right here is the MAC value. Okay, the value of MSE, and you can see that here is the minimum point of MSE. Okay, it should be some certain A star and B star, right? That is the best MSE value. Okay, and you can see that in this, we say in this basin. Okay, in this basin, because we have a very large MSE value. Okay, the A exit. Okay, you can see that the value is quite large, right? It's quite large. So when we perform gradient descent, usually, okay, we randomly pick some A0, B0 value as the starting point, right? And then as you can see that at the A direction, okay, because it is very large, those are very large value. So the slope of A direction will be very large. So for gradient descent, you can simply just go to the bottom of this basin at the A direction very quickly, right? Because the slope is very large. But take a look at the B direction right here, okay? The B axis right here. And you can see that it seems like there is very small slope in B direction, in B axis, at B axis. So even if you already at the bottom of A axis, but the B direction, okay, the B axis, the slope is very small. So it takes you some time and a lot of different steps to figure out where is the smallest value of MSE. Okay, the reason why this basin looks so weird, that is because, okay, it's right here. It's because this one. If we use the original data point, then the MAC value was something like this one. Okay, we use the value of x1 and y. I think there should be some 30 plus that point right here. Okay, we use this 300. I think it is 300, right? Okay, right here. We use those 313 data point, right, of the data. Okay, we use the original data point, and you simply just put it into your MAC function. Okay, you can see that the coefficient right here, they are quite large. That's because your x value and y value, they are large. Okay, so that indicates that when we do gradient descent, okay, this part will be very, we say, large. Okay, so when you perform gradient descent, okay? And as we mentioned, that is the learning rate, right? And that is the step, okay, the direction and the how far you can go on the on certain direction, right? That would be large. So it is a little bit difficult for you to find the minimum point of MSE. Okay. So as you can see that is large, but that is quite small, right? So the direction of theta 1 and theta 0, the value right here, okay, for the theta 1 that would be large, for the theta 0 that would be small. So the step right here for the theta 1 direction, the step would be quite large, and theta 0, the direction of theta 0, to find the optimized theta 0 star would be slower because the step is quite slow. So that is not that good. Okay, so if you perform normalization first, and you can get x prime and y prime. So it looks like that the range of x prime and y prime, they look much better, right? They all between 1 and 0. Okay, so if you use this value to right here, so if you use scaled data point, and you can see that the slope, the value right here, they are not as big as the coefficients in the original MSE, right? So the basin of MSE looks like this. That's quite good. Okay, and you can see that here the number right here is smaller, right? It's smaller, so the slope is smaller, and you can see that there's a basin right here. So even if you randomly select a A0, B0, okay, and when you perform gradient descent, it is much easier for you to find the smallest A star and B star right here, because this basin is smaller. Okay, it's smaller, and you can easily find there's a gradient right here, and the gradient right here is not that big. Okay, so that's the reason why we must add one additional normalization layer after your input layer. So again, okay, so here we like to introduce how to so we stop right here. We'll talk about how to perform how to make a neural network model by using Keras.